Sí.
Ya no sé nada.
Good afternoon, everybody. Okay. From here with the Neuroscience group after the lunch. You have to imagine you have to focus on what you are telling you. It's a response. He has been mechanical engineering and PhD in physics, and he's the head of the group of the Neural Institute. We have also we are focused mainly in neurorobotics. Here, and well,
Thank you. Can you hear me? Is it okay? Okay, so thank you, Guillermo, for the introduction, and thank you to the organizers for inviting me to come here to share with you our research activities. So the title of this presentation is how we can exploit brain plasticity in order to manage neurological conditions, mostly with wearable robots and motor neural processes. Okay. So this will be the outlook of my presentation. So there will be three main blocks. First, I will introduce, motivate our work at the Neural Rehabilitation Group. Then I will be touching different areas where we work to develop these technologies, use these technologies for rehabilitation and to assess also the conditions of our patients. And then our vision in terms of which specific new neural rehabilitation and therapeutic methods we are proposing based on this. You will see along the different slides these symbols here. So this is because I will be referring to neurological conditions that have effect on the mobility of the upper extremity or lower extremity. And I will be touching basically three conditions: strokes, spinal cord injuries, and neurodegenerative conditions like Parkinson's disease and essential tremor. So as Guillermo introduced, we are based in the Cajal Institute. Cajal Institute was founded something like 85, 90 years ago. It was founded by Santiago Ramón y Cajal. When we came to the Institute 4 years ago, there were two different departments, both on basic science, molecular, cellular, developmental neurobiology, and functional systems neurobiology. Then a third department on translational neuroscience was created. And our group, the neural rehabilitation group, sits in this new department. So basically, what we want to do is to develop technologies that can help us understand the mechanisms of motor function in general. We also touch several activities related to cognitive function, but mostly motor, and how we can use these technologies in the clinical setting to promote neurorehabilitation. So we have a large network of collaboration, mostly through European projects. So there are two, let's say, main activities that we have been focused on during the past years. One is related to neurodegenerative conditions, and there were a number of European projects on this topic. The last one was neurotremor that we coordinated like 3-4 years ago. And then there is another big research activity which is related to neurorobotics, exoskeletons, and how we can use them for promoting rehabilitation of locomotion. And this BETTER project is one of the European projects that we have in this area. We have collaborations with industries. Here you have just a few of the industries with which we collaborate, Osur, Philips, and also with European universities. We have a special collaboration with Imperial College London and also with Aalborg University. So until 3 months ago, we had 2 ongoing European projects. This one here is on multimodal technologies to explore brain activity. So we here are trying to combine EEG electroencephalography with near-infrared spectroscopy in order to evaluate the condition of the patient and how we are inducing changes in the brain activity. And this one here, which is on lower extremity exoskeletons, this is a close-to-market project where we transferred the technology to a local company here in Spain. So during this project, we were, let's say, supporting these companies to bring the technology to the market. So starting January this year, we are coordinating 3 additional European projects. This one is a coordination support action. So basically, here we are studying and addressing non-technical barriers for the uptake of these technologies by the society. Here we are trying to develop a framework for benchmarking and evaluating technologies for neurorehabilitation. And this one here is especially focused on how we can interface the human central nervous system with assistive technologies in the process of rehabilitation. So I will be, as I said before, focusing mostly on 3 conditions. 2 of them are stroke and spinal cord injury. You have here examples of patients with this condition. So in general, we can say that conventional therapy is in many cases not sufficient to restore functional capabilities of these patients. So we need novel therapies, and we think that through robotics and neuroprosthetics, we can have a high intensity, repetitive, task-specific practice that could lead, if we use it properly, to promote motor recovery. Another condition that I will be touching upon this afternoon is Parkinson's disease and essential tremor. So as you know, these are neurodegenerative conditions. They are highly prevalent. It is recognized that it is the most, so the tremors resulting from these conditions are the most extended movement disorders. And basically, there are 2 ways of managing these conditions, either through medication, drugs, or through DBS, deep brain stimulation. So basically, both have side effects. So we thought that with the technology that I will introduce in a minute, we could provide an alternative to both medication and deep brain stimulation. Overcome this. So it is a bit dark, but what you have here is three examples of three different patients with essential tremor. So this is a very low tremor. This is a medium one. And this is severe. So you can see that tremor is really very disabling, especially when you have moderate to severe disorder. So this is one of the motivations that we wanted to develop these technologies to try to manage these conditions, trying to reduce tremor so that they can have improved quality of life. Okay, so in a nutshell, we develop in our group three different types of technologies, and they are targeting motor restoration. It's the primary goal here is to promote the recovery of motor function. We have also technologies for motor replacement. So this means that when we cannot recover or promote the recovery function, then we compensate for that function with the technology. And then we have other technologies that we use in sort of neuromodulation approach. I will come to this in a minute. So the first, an example of this motor restoration technology is the exoskeleton that we have here in this video. This is a video taken during clinical trials in Houston, in Texas, at the Tier Memorial Hospital. So the idea is that we use this technology in a training protocol with stroke patients, trying to promote changes in the brain activity and in the different structures, bodily structures, to try to promote motor learning. Okay, so the idea, so we are using here the technology, the EEG cap that you see here, not to trigger the operation of the exoskeleton, but to look at the brain activity and to see how it changes according to the functional improvement. So the way we have here to interact with the patient is through the exoskeleton technology, and then the way we have here to assess motor function and improvements in motor functions is through clinical scales plus neurophysiological studies, for instance, by looking at deep an example of this motor replacement is this exoskeleton that you see here. So this is a patient with post-polio syndrome. So here it is in the chronic phase. There is no room for improvement. So the idea is to use the technology to compensate for the lost function and to have a more natural locomotion pattern for this. And then the other example of neuromodulation is shown here. So you have here the same patient with a neuroprosthetic device. So I will come later on to this, but this is basically functional electrical stimulation of some muscle groups. So the idea is that we can have the system off or on, and with the proper strategies, we can suppress or reduce the tremor level. So this tremor level would be incompatible with, for instance, drinking with glass. This tremor level would be compatible with that activity. So the idea would be to use the technology to neuromodulate, change the CNS in order to promote or to reduce tremor in this. So of course we don't do it ourselves alone. We collaborate with a number of hospitals. So for instance, for most of our activities related to spinal cord injury patients, both upper and lower extremity, we collaborate with Hospital de Parapléjicos de Toledo or with Goodman Institute in Barcelona. We have a strong collaboration for strokes with Tier Memorial Herman in Houston for the lower extremity, and CEADAC here in Spain, in Madrid, for the upper extremity, and with Fondazione Santa Lucia for both upper and lower extremities for patients. And when it comes to collaboration for the Parkinson's disease and this type of conditions, for the upper extremity, we mostly work with Hospital Gregorio Marañón. And for for the lower extremity and for the upper extremity, we work with Hospital 12 de Octubre and here in Spain as well, and Hôpital Erasme in Brussels. So, so this was just a summary of our activities. We also organize different training and scientific meetings. So this is a summer school that we organize every year in September on neurorehabilitation. This year it would be the 8th edition of this conference, and these are an international conference that we organize every second year on neurorehabilitation, and the conference that we organize every year on wearable robotics, mostly for neurorehabilitation. So this was just as a sort of introduction of our activities. Then I will go to briefly touch upon a number of activities that we are using to try to promote these changes that will reflect in changes in CNS. So I think one of the technologies that is, at least I think we are mostly known of, is wearable robotics. So we started our activities on wearable robotics like 20 years ago. This is a book that we published 10 years ago. So in this book, we were looking at the different disciplines that need to be integrated in order to develop these technologies and to use these technologies in novel rehabilitation methods. So, for instance, here we had neuroscience, biomechanics, mechatronics, signal processing, and others. So the idea is to understand how all these domains can be used in order to develop these technologies and how we can use bioinspiration. When I say bioinspiration, I mean not only to develop the structure of our robots, but also to understand which are the mechanisms that we implement, for instance, for walking, and we replicate those for the control strategies of our. So this is the first exoskeleton that we developed like 15 years ago. You saw already the video before. This is the post-polio syndrome patient. This is a fully passive exoskeleton. There is no energy consumption in this device. So it is fully passive. It is spanning the ankle and the knee. And behind the design of this device, we had to model the anatomical joints in order to have a kinematically compatible exoskeleton joints. We had to model the musculoskeletal response of these patients so that we could design passive actuators that could complement the missing force that these muscles can produce. We had to design the structural components of our systems so that we have a similar mass distribution as the one that we have in our limbs. Because one of the things that we benefit from when we walk is the perceived dynamics of our limbs. So if you modify, for instance, the mass distribution of these limbs, then you cannot expect walking as if you were not using an exoskeleton. So you have to design this by keeping, for instance, this analogous mass distribution. And of course, we had to develop sensory and control strategies to be able to manage this device. So what we have at the end is something like this. So this is a phase diagram of this exoskeleton. So the idea is that we have the user, the patient, and the exoskeleton working in what we call a limit cycle. So this is with really very low energy input, but it is this limit cycle is not stable. So if you have a robot, just a robot, with a limit cycle control, and you perturb it by pushing it, then it will fall because there are no mechanisms to recover. But here we can benefit from the fact that we have in the loop human with a hip control that can compensate for perturbation. So we have the benefits of low energy consumption with the exoskeleton, and the benefits of, for instance, keeping balance that is provided by the patient. Okay, so this is just a technology that we patented a few years ago, and we transferred to a company in Iceland. They are still thinking of whether they will commercialize it or not. So one of the things that is interesting to mention is that you can build many neurorehabilitation protocols out of these technologies, but then you have to be precise and accurate in assessing which is the effect that your technology will have on the patient. So this is a paper that we published a couple of years ago. So here it was a review paper. We were looking at the use of these technologies in spinal cord injury patients, and we were looking at which are the different dimensions that are used to evaluate the effect of the technology on the motor restoration of these patients. So when you look at the different dimensions, you have most of the metrics which are clinical scales related to function and to balance. You have a few metrics or indicators that are focused on physiological aspects, and then some of them most focused on usability and energy consumption. So out of this paper, we learned a couple of lessons. One is related to how we can design protocols that are more effective in promoting the changes that we want to promote in patients. And then the second one is how we can complement all these metrics in order to have an assessment on the internal changes that we are inducing in the CNS, for instance, plastic changes at different levels. So this is the latest, or the not the latest, because this is H2. We have H3. This is the latest exoskeleton that has been that has been used in a clinical trial. You saw a video before. This is again in Houston. It is a light exoskeleton. It is bilateral, so this means that it is assisting the patient in both legs, the ankle, knee, and hip. It is an open architecture, so you can easily network this technology with other medical equipment, for instance, to assess changes. And it has been intensively tested on stroke and spinal cord injury patients. So if you look at these are group data of a few patients, I think 6, 7 patients in Houston. It is difficult to see, but what you have here is the session number. So they were subject to 12 training sessions in 4 weeks. And this is the total number of steps that they can walk without the exoskeleton. So you can clearly see an improvement in the distance that they can walk without the exoskeleton as the training goes on. And the same happens with speed, with the walking speed. This is speed steps per minute. So you can see also this. But maybe what is more interesting is that because we have this EEG cap in the users, we can record EEG activity, and then we can estimate out of the EEG activity the kinematics of the locomotion. So we can estimate angles, hip, knee, ankle angles out of the EEG activity. And when you correlate this estimation with the real angles that you measure with the skeleton, this is the correlation coefficient between these two kinematic estimations and actual reading. And what you see is that this correlation coefficient is improving along sessions. This suggests that the brain representation of the locomotion process is improving along the training phase. It is not just that we are improving locomotion because of they can walk longer distances or faster. It is also that we are promoting changes in brain activity that are correlated to the function improvement. So this is an indirect way of assessing internal changes that are consistent with functional changes. So, but we can use the technology not just as you saw for locomotion. So if you use just the ankle version of the exoskeleton with stroke patients, you can, with this technology, propose different interventions, different protocols to try to improve other aspects of the condition. So, for instance, what you will see here in this video is in Rome at the Fondazione Santa Lucia that we are using the ankle version of the video of the exoskeleton that you saw in the previous video to try to reduce spasticity. Spasticity is a condition, as you know, that results in rigidity of the different limbs. So instead of using this for walking, what we are using here is a protocol where we use the exoskeleton, the ankle version of the exoskeleton, to assist plantar and dorsal flexion. At the same time, we record EMG activity and we provide feedback to the patient on the coactivation of antagonistic muscles here. So it is a complex protocol where we combine assistance, recording feedback, and sort of operant conditioning, because we ask the patient to keep this coactivation level low. So we conducted an experiment for a sort of pilot clinical trial with 10 subjects in order to see the effects of this condition. And when we look at indicators of spasticity based on the modified Ashworth scale, we have clear reductions for the experiment. So this is just another example of how we can use the technology for these patients. So I will now jump to the other condition, which is Parkinson's disease. So this is the second exoskeleton that we developed like 14 years ago. It was an upper extremity exoskeleton, and the idea was to provide this alternative treatment for tremors. So instead of having deep brain stimulation or medication, we knew from literature that when you load the limb with weight, the tremor is reduced. And this is exemplified here. So this is the time signal related to tremor. This is the frequency content. And this is exactly the same for a patient where we have added some weight to the upper extremity. So you see that there is a reduction in the energy at the tremor frequency. So you can use this principle. You can load the limbs to reduce tremor. So this is what we try to use to do with this technology. So this is just a panel to show the results of this was a project, 3-year project, a European project. So this panel shows the results of this project. So what you have here is the severity of the tremor. So these are more severe tremors, these are less severe tremors. And what you have here is that the tremor suppression. So 100% means that we did nothing. And any of these patients here below 100% means that we reduced tremor. So the interesting thing here is that for most of the patients, we reduce tremor. For all severe cases, which are the ones that are compromising the quality of life of our patients, we have also a tremor reduction. The problem with this technology is usability. So you cannot expect that the patient would use a device like this that weighs 3+ kilos just to have a reduced tremor. But this experience learned or indicated to us that the principle was okay. So we looked for alternatives. So instead of using robots, next step was to use neoprosthetics and hybrid robots and neuroprosthetics. So this here is the slide summarizing the results of the second project that we have in tremor. So what we did here is we tried to reach the same results that we had before, but with this device, which is a neuroprosthetic device. It is a textile-based device. So we have in this textile electrodes. With these electrodes, we can record muscle activity. we can estimate the motor status of the patient, and then we can use the same electrodes to stimulate the muscle to see whether we could have similar results. So these are just several examples. So this is a patient. This is another patient. This is the tremor signal without the neuroprosthetic device on. As soon as we start the neuroprosthetic stimulation, then tremor is reduced. This is also seen in the frequency content. But again, this panel here is summarizing the results of the different projects that we involved. Sorry, different patients that we involved in this project. So again, this is tremor severity. This is tremor attenuation or suppression. More severe tremors, less severe tremors, nothing. And this is tremor reduction. So again, this is similar to what we had before. No difference in terms of performance. The main difference here is that now we are using a device that is based on textiles and that you can wear underneath your sleeves. So this was the second project that we had on these conditions. Then in this second project, by serendipity, when we were, this is me, this is in Brussels. We were calibrating the system that I was showing before for this patient. Then we realized that this patient, the tremor of this patient disappeared when we had very low stimulation below the motor threshold. So it is not that it was not in that particular case that we were driving or stimulating muscles to counteract tremor, but we were using another mechanism that we didn't know of, by which when you stimulate afferent sensory cues, you also reduce tremor. So this is why we started a third project, just to understand which were these mechanisms and to see how we could use them. Because if we can suppress tremor peripherally without stimulating muscles, then we have a huge advantage. Because if you use stimulation for muscle movement, then you fatigue muscles. But if you use stimulation just below motor threshold, just for afferent cues, you have no muscle fatigue, and you could potentially have also the same results in terms of function. So we started the third project. In this project, we, together with the Fraunhofer Institute in Germany, we developed implantable technology. So the idea is that with this implantable technology, we could compare with more, looking for a word, with more accuracy in targeting fibers. It is implantable, it is not superficial. We could compare motor versus sensory strategies to suppress tremor. We could test sequential versus simultaneous recording and stimulation strategies, or we could also compare implantable versus superficial. So this is, I don't know if you will see, yeah. So this is just a video summarizing what we did in this project. This is here in Madrid, at Hospital 12 de Octubre. So this is the technology that we developed. It is a thin film implantable microelectrodes for recording and stimulation. It is implanted by means of a needle. So with the needle, you put the electrodes close to the muscle belly, and then you cut a mechanical link that is linking the needle to the electrode, and then you extract the needle, and the electrode sits inside the muscle. Okay, so with this technology, then you can connect to all the electronics outside. With this, you can have access to EMG activity. Out of this EMG activity, you can estimate the status, the motor status of the patient, and then you can use the same implantable device to stimulate both motor or submotor cues to see which is the effect of on the tremor reduction. Okay, and then you can, of course, there is an application interface to modify all the different parameters for this stimulation. Good. So we patented also this technology, and we transferred it to another company in the States, Health. This in Stanford University, and we are now in the process of trying to commercialize this technology. So I have shown robotic devices and prosthetic devices. So what about the combination of both devices? So here we have an example of this. This is here in Madrid at FEADAC. So this is an upper extremity robot. It is a commercial one. So we used this commercial robot, and then we developed the functional active stimulation part. So we have now two systems, robot and neuroprosthetic device. And then we can orchestrate the contribution of both of them in order to assist patients, these are two-stroke patients, doing upper extremity motor training. The difference between this video and this video here is that here you see an EEG cup, and here we see you see nothing. This is because we can interface the technology, the robots, and the neuroprosthetic device to the patient, either by looking at the brain activity, or like in this case here, or here by looking at the muscle activity or to the residual movement of that particular patient. And then we can assess, for instance, during these interventions, which are the effects that we have by, for instance, looking at the motor evoked potential in different muscles that we are targeting here as a result of TMS, transcranial magnetic stimulation. Another example of a hybrid system is this one here. This is in Toledo, at the Hospital de Parapléjicos de Toledo. And this is the same as before, but it is a combination of lower extremity plus functional active stimulation. So you clearly see here different electrodes, the structure, and the training protocol. Good. You have probably noticed that one of the key components of all these technologies is how we interface the technology. So I will be just touching upon a number of examples on how we can conduct these interfaces. So we think that the interfacing with the patient is key because of many reasons, but mostly because it is key in order to obtain natural operation. I mean the robot, the neuroprosthetic device, should nicely respond to my intentions. If I want to move my limb, my upper extremity, I would expect that if I want to do this, the neuroprosthetic device or the robot, in a way, knows that I want to do this and then assists me to perform this activity. It is also very important because we can use the interface to establish causality between motor planning, brain level, with the assistance that we provide with the devices. And also because it will help to promote embodiment. So map these technologies into our motor program. So this is key. The idea is to source the information that we need for these interfaces from a number of stages. So we can source it from brain activity, spinal activity, muscular activity, or motion activity. And I will show you several examples of this. Before, I wanted to briefly introduce one of the concepts that we are trying to promote in our group, which is the concept of associative intervention, which is exactly what I was saying before. So we have motor planning stages at the brain level. So we can try to decode those motor planning stages out of brain activity, for instance. And then as soon as we decode this motor intent, we use robot, neuroprosthetic device, to provide some feedback, and this would close the loop. Okay, so the idea is to try to promote motor learning by closing this loop. This is based on previous results that I will not address in detail that indicated that when you have association between different stimuli, peripheral and central, then you can potentiate or facilitate different pathways. But I will not go into detail. in summary, what we have is in healthy people, you have brain activity. This will be translated to the muscles, and then you will have, for instance, this limb flexion. When you have a stroke, this brain activity is, in a nutshell, disrupted. So they cannot reach, at least with the same intensity as healthy people, the muscles. So the idea is to use interfacing technologies to decode this brain activity, which is preparatory for motor actions, and then use the technology to close the loop. So the idea would be to try to identify this activity. With this activity, we decode the intent of the user, and then we use, for instance, functional activity stimulation to stimulate the muscles and then close it. And if we do this in a causal and synchronized manner, then we can expect to improve motor function. So I think yesterday you had the opportunity to look at different ways of how you can process this EEG activity, for instance. I will very quickly go through this. So one possibility is to look at slow cortical potentials. So if you look at brain activity over this area here, which is the central part here, and you average several movements, you have, and you filter them out, you have a sort of signal like this one here. So the challenge here is, out of this information here, single trial, real time, try to identify these signals as soon as possible so that you can trigger the operation of your robot in a synchronized manner with the natural movement. Okay, this is one of the possibilities. The other possibility is using sensory motor rhythms. Here again, this is the situation where you have several movements and then you filter them and average them. You have an event-related desynchronization and then synchronization that is related to the motor activity. So if you could identify this pattern here out of this activity, single trial, real time, then you can ideally trigger the operation of the system in a synchronized way. So, so what we did in the past in our group is to use both paradigms, so slow cortical potentials and event-related desynchronization in a sensory fusion approach to try to have a robust decoding of brain activity related to motor intent. So I will be showing here just an example to see the difference between causally timing brain activity to the assistant or not. So this is a stroke patient. This is here in Spain at Hospital de Fuenlabrada. So what we have here is EEG cap. So we are trying to conduct this decoding real time. So we are looking at the brain activity. Whenever we detect an activity, a brain activity that is consistent with motor preparation, then we use these electrodes that you see here to provide coordinated assistance in different muscles. So the idea is to help this person to reach with the left arm this target here. So he cannot do it alone. And the functional activity stimulation that we are providing cannot move the limb alone. So you need the contribution of both the patient and the functional activity. So you will see first, so this is a first trial. So we detected brain activity and then we assisted, and then he reached the target. You will see now a second, sorry. You see a contraction here without a movement. Let me play again the video. So the first trial is a success. So we detected brain activity consistent with motor intent, and then we assisted, and then he completed the motion. The second trial, you will see only a muscle contraction without a motion. So this is the first one. So you have the contraction and then the motion, and then you will see another trial in a second here, where you saw muscle contraction but without a movement. This is because this was a false positive of our EEG detector. So we thought that he was planning a reaching movement, but he was not. So we delivered the functional assistance with the neuroprosthetic device, but he was not contributing. So this is why he couldn't reach the target. So this means, or this exemplifies how you need to associate the motor status to assistance that you have in order to promote the training. So if there is no contribution from the patient, there will be no motion. And this is what I was referring to, associative interventions with this closed loop. Let me quickly go to another example, which is related to the tremor patients. So we have been focusing on EEG, but we can also source information from other electrical signals. So, for instance, we can look at EMG, which is muscle activity. So, in this particular project, we were using high-density EMG. This means that we had a number of electrodes on the same muscle. So we had different EMG signals coming from the same muscle, but from different electrodes, which were very closely located one to with respect to the other. Okay, so with this information, we have a number of EMG signals with blind source decomposition techniques in cooperation with other groups. You can decode the motor unit firing, which are stimulating that. So this means that from EMG activity, you can decode the last stance of the neural activity, which is the firing of motor neurons, the muscle. So if you do this with a healthy volunteer, then you compute time between different consecutive firings. You will have a situation here. So this is a histogram. This is this time between consecutive firings. So there is no asynchronization on the firing. If you look at a patient with a Parkinson's disease or with essential tremor, this is the situation that you will find. So you will have a clear synchronization of these firings. So with this information, you can detect tremor onset. So when you pass from this situation to this situation, you can say that tremor is now present. And with this information, you can track different tremor parameters, like frequency, amplitude. Okay. So then the last thing that is missing is to see whether all this information is consistent along the CNS. So here you have different panels. So here you have in black the EEG activity in one of these electrodes, and in red you have the brain activity related to tremor. Here you have the tremor component, the motion component of the tremor. Here you have the different motor unit firings. So when you compute the power, the frequency content of all these signals, then you have a clear peak here, which is the peak that you have tremor frequency. So you have consistently assessed tremor along the different stages of the condition. So so how long do I have?
Yeah, 15 minutes.
15 minutes. Okay. So so I was addressing EEG, EMG, high density EMG. The same can be done, and the previous example it was for tremor. The same can be done to trigger the operation of lower limb. So here, when you have a patient with an exoskeleton, you have immediately two sources of information. You have kinematics out of the exoskeleton, and then you have EMG information from the patient. So, so with models, with neuromusculoskeletal models, and with these two informations, you can predict the force-producing capabilities of a patient. Okay, and if you predict the force-producing capability of a patient, and you have an estimation of what are the needs for a healthy walking, then you can compute what we call the capability gap, which is the difference between what is required and what the patient can develop. So with this information, with the capability gap, you can command the exoskeleton to deliver the assistance that is needed. Okay, so this is just an example to see how this can be done with a stroke patient. Now we have the exoskeleton outside the patient, just for you to see the operation of the system, but we are using this information to trigger the operation of the exoskeleton. And what you have here is the ankle version of another exoskeleton that we developed in the BioMod project, where we were computing real time this capability gap. This is a healthy volunteer, but this capability gap with information delivered by EMG sensors and by these kinematics. And then if you have this situation, then you can compute. This is for healthy people. You can compute EMG that you need for walking without the exoskeleton with the energy that you need to input with an exoskeleton that is assisting you. And you see this in the muscle activity that is low for the use of the exoskeleton. I will just skip this one here and go directly to a number of aspects related to how we can assess neurophysiology, motor control aspects, and neuromechanics and biomechanics. So the brain, spinal cord is involved in a number of aspects related to walking, to locomotion, and to other functions. So one of the aspects is balance. Okay, so and this requires the CNS to orchestrate a number of muscles in a coordinated way. So exactly like we did before, in which we correlated changes in brain activity to functional improvements during locomotion with stroke patients, we can look at how different muscles are coordinated to see whether we are having an impact on the balance capabilities of our patients. So for this, we use a mathematical tool that is what we call muscle synergies, which is a decomposition of the EMG activity of a number of muscles into two components, muscle activation component and weight component. So basically, what we are doing is, for a given function, we record EMG from a number of muscles, and then this EMG is averaged and then decomposed into muscle activations that are supposed to be supraspinal and muscle weightings that are supposed to be written in our spinal circuit. So these muscle activations are transferred to different muscles according to this weighting. Okay, so this tool can be used to estimate muscle coordination, and then we can compare, for instance, a healthy volunteer doing overground walking, and the same healthy volunteers with a robot-assisted walking, and to see whether the fact of using a robot is changing the way you coordinate your muscles. Because imagine that just because you have a robot, you are coordinating your muscles in a different way. Yes, then you could question whether this robot is helpful for rehabilitation. So we conducted these experiments in a paper a few years ago, and then we concluded that at least the exoskeletons that we were using we're not changing the muscle coordination of our patients. Then you can also question whether, depending on, for instance, it is difficult to read. Here we have different walking speeds and different assistance levels with the exoskeleton. We can see whether this muscle coordination is changed between conditions. And again, in the same paper, we concluded that this is not the case. So this is a validation that an exoskeleton can be used for rehabilitation. And that these muscle synergies can be used to estimate the effect of rehabilitation on muscle coordination. Let me come back again to the Parkinson's disease. So remember that we had high-density EMG electrodes in a number of muscles. So one thing that we can do is we can compute this motor unit decomposition in antagonistic muscles. And then we can compare the phase between these signals in the different muscles. So if we do this for postural tremors are Parkinson's disease tremors, we see that antagonistic muscles are mostly out of phase. If we do this for, postural tremors are essential. If we do this for resting tremors, like Parkinson's disease, we see that the signals are mostly in phase. This means that this could be an indicator that can be used for an early diagnosis of tremor. I will come in a minute to this. We can also look at the ratio between the first and the second harmonic of the signals that we are recording with EMG, high-density EMG. If we do this for Parkinsonian patients, this ratio is high. If we do this for essential tremor patients, the ratio is low. I'm saying all these things because we can complement clinical evaluations by neurologists on people with symptoms of tremor with this non-invasive tremor monitoring. For instance, this phase between antagonistic muscles, or this ratio between harmonic, to provide additional information that can be used for an early diagnosis of tremor. One of the problems in early diagnosis of tremor is that roughly between 30 and 40% of the patients that are diagnosed as a condition along the time are re-diagnosed for another condition that is also leading to a similar symptoms. So this was part of the third project that we had in tremor in tremors, and we were monitoring patients, around 120 patients for 4 years. When we finished the project and we ran all these indicators on the data set of patients that we had, we identified with 2 years in advance changes in this diagnosis with respect to the actual change in diagnosis by neurologists. This could have a huge impact on, for instance, on the medication that is the treatment that these patients are subject. Okay, I will skip a couple of slides and then go directly to the last part of the talk, which is our vision. We can use all these technologies in clinical. So this is related to what I said already at the beginning. So we need, in addition to clinical evidence, we need to complement the assessment of our patients out of this bunch of technologies that I was showing, where you can have access to changes in the CNS and PNS you are promoting with the technology. So one of the things that we want to do is to use the technology to support the assessment of neurorehabilitation protocols and to support diagnosis of these conditions. Another very interesting aspect is related to patient profiling and personalized medicine. So if you could use these technologies to have a more accurate estimation of the motor status of this patient, then you can, for that particular patient, propose a combination of interventions that would facilitate motor. And here we have a bunch of technologies and approaches to try with patients. We can use drugs or brain stimulation to try to facilitate plasticity in several areas. We know that with robotics and neuroprosthetics, we can promote brain plasticity in in primary motor cortex. We know that with virtual reality and with feedback and with operant conditioning protocols, we can also target the regions. So the idea would be with information from clinical assessment plus the information from the technology, we can profile our patients and design specific interventions to personalize the medicine. I think we also need to improve the way we use technology for assessment. So, for instance, in several of the studies that we are conducting in our group, we use TMS, motor evoked potentials, to assess the corticospinal excitability during the intervention. So this is just an example, but there are other techniques that we can use to have an accurate estimation of what particular mechanisms we are triggering during our interventions. And finally, of course, we will keep developing new technologies. You have seen that one of the key aspects of all these technologies is interfacing with the human subject. We have now a specific project that will take us 4 years to develop this technology. So this is the concept that we have. The idea is to develop tiny implantable devices that can both record and stimulate, and that can be activated from the outside, so that we can distribute these tiny devices in different muscles, so that we have a sort of network of pickups where we can source information on motor status for the upper extremities, for the lower extremities, and then because these devices will also have the ability of stimulating the muscles, we can close the loop, for instance, to suppress tremor. And this, with respect to what we did, would allow us to have distributed management of tremor. Before I didn't say it, we were just targeting one single muscle with one single electrode. If we had a number of muscles instrumented with this technology, in principle, we can distribute or we can control in a distributed manner the tremor. Or, for instance, if we have a number of electrodes in different muscle groups in the lower extremities, we can extract information, compute the capability that I was referring to, and then use an external device, an extraction, to provide the right assistance to the patient. And this technology that we are developing with Imperial College, with Universidad Pompeu Fabra, with a couple of hospitals here, will be a breakthrough, because it is based on a novel concept for passing energy to the devices, which is not inductive, where the technologies that we had before, this one here, but it is based on rectifying high frequency electrical currents we can use externally. So with this, I finish. When I was saying we did, I was not referring only to our group, but to say the groups that typically collaborate with us. So this is just the team of one of the projects that was responsible for developing the lower exoskeletons that I was showing in the videos. So here we have people from Hospital de Toledo, Hospital de Fuenlabrada, different institutions. So of course this is the contribution of all these Yeah, no, not really. So what we have been doing, I didn't went into all the details, but behind this strategy to use some motor threshold cues, there was a study where we identified that the effect that we were causing was trying to disrupt the amplification that at the spinal level is done specifically for each patient. So with this stimulation, we are just trying to disrupt this amplification, and this is the cause of the reduction that you saw in the video. So we just conducted a number of pilot studies with several patients, and now we are with this company in the States trying to let's say continue the development of the technology. So yeah, so if you have a false positive, then you cannot reach the target because the functional stimulation is not enough to move the limb. If you didn't detect the intention, then the man will use compensatory movements to try to reach the target. So it will not be a clean movement of the limb, but it will be a compensatory movement of the whole trunk trying to reach the target. So we still don't know which is the minimum numbers in terms of how many errors you can allow to have a motor training effect. With this technology and with stroke patients, we were around 65 to 70% right detections of motor intent, which is I think good. So if you go to healthy people, the numbers are much higher. But with these patients, so in some patients you cannot detect anything. But for the ones that the technology is working, you can expect a level like 65 to 70%. Yeah. So to your first question, I would say I have no idea. I don't know if we can use this functional stimulation to try to recover from this condition. So as related to the second question, whether with the technology we can induce maladaptations or wrong strategies for rehabilitation, this is possible, of course. This is why we were, for instance, evaluating which is the effect of exoskeletons on balance and on motor coordination in healthy people to see whether we can expect a bad effect on patients. But yes, the question is yes, you can use the technology in a wrong way, and then you can lead to bad results. Thank you.
Mientras el profesor Gustavo Deco prepara su ordenador, habíamos pensado en hacer una foto de todos juntos, un recuerdo de Green. Entonces, si queréis, podemos ponernos aquí. Entonces, si lo hacemos rápido. Podemos subirnos encima del escenario, porque si no vamos a acabar. Cuidado con los cables, por favor. Como que vamos. Bueno, yo creo que en 2 niveles.
Mira, voy a.
Pon un cartón de un abrigo, profesor. Un abrigo.
Estupendo, traemos todo. Está todo grabado. ¿Alguien ha perdido los bits? Debería estar encendiendo. ¿Vas a querer el micro de pie? ¿Quieres hacerlo sentado?
No, parado.
Sentado.
No, parado, así, parado.
Conmigo, hermano.
Sí. ¿Se necesita el micro?
Sí, para la grabación. Voy a dar por primero que sea el otro micro. Voy a mirar, ¿vale? A ver cómo va la batería. Bueno. Dentro recibimos señal. Sí. Vale, voy a comprar una cosa. Sí, 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 sí. So the next talk is Professor Gustavo Deco from the Pompeu University in Barcelona. I have to say I tried to do a fair introduction, but when I saw his CV, it's like 100 pages, so it's more than my master thesis. He did his first PhD in University of Rosario in Argentina in physics, and then he moved to Germany, to Munich, and there he did another 2 PhDs in computer science and in psychology. So yeah, nowadays he's working. He has a research group in the Pompeu University in Barcelona about brain and cognition. So thank you so much for coming here, and yeah.
Yeah, thank you so much, Jose, for the introduction, especially for inviting me. Can you hear me? I don't have the impression it's working. Yeah.
If there is.
Okay, so my goal today is to give you a relatively brief overview of large-scale modeling. So my main aim is really to construct and to show you how we can construct mechanistic models at the level of the whole brain. Just to give you, let me start with some motivation. I know that you already heard something about resting state, but we decided 10 years ago to start this type of business or whole brain modeling, departing from the use of resting state. Nowadays, of course, it's much more general. I mean, we can do whole brain modeling not only restricted to resting state, but to other different type of brain states like sleep and so on. And I will show some of those examples, or even under the execution of some perceptual or cognitive. So, but just to motivate the beginning, I mean, why we were at the beginning interested on resting state for constructing this type of model, let me try to give you a very general, cartoonized type of motivation about the origin of resting state. As you know, I mean, this is our problem. We want to understand this particular black box, which is the brain, and we would like to understand how that works from a mechanistic point of view. What are the mechanisms underlying different type of brain function? And the standard strategy, as you know, which is common in science and was extremely successful in physics, chemistry, and so on, is what we call inverse modeling or reverse engineering. And the idea is extremely simple. I mean, you have your black box, it's the brain, and then you start to stimulate the brain with different inputs. For example, different type of visual stimulation, auditory stimulation, performing different type of tasks, and then you characterize how the brain reacts, also at very different levels. And this is the beauty of neuroscience nowadays, that we have a lot of technology that allows us to characterize the brain at the behavioral level, at the global activity level, with fMRI, EEG, MEG, your favorite technique, optical imaging, or even at the microscopic level of single cells. And by trying to establish the relationship between this input-output reaction, we can infer something about the underlying mechanism. And that was also in neuroscience. That most of the things that we know in neuroscience, at least in the last centuries, was gained by using systematically this type of philosophy, so reverse. Of course, we are assuming for the use of this strategy that in the absence of any kind of stimulation, that is what we call resting state, actually not the best semantic for designing this type of condition, but let's say in the abstract situation where we don't have any kind of inputs, we are assuming that the activity of the brain is really at the background level. And what this means is a minimal energy is not activated or is activated in a noisy way. So there is no particular spatio-temporal structure. And because we don't have a very particular spatio-temporal structure, then we can concentrate on the structure that we generate by applying some inputs, the relationship between input. Of course, if that is not the case, we have a problem, because if we have some spatio-temporal type of activity, and this is what I will show with this video, not using the brain, but using a much more simple system, which is the system water, we need to take into account then the spatio-temporal type of structure that we have under resting condition. In this case, as you know, the physical system water has a perfect resting state. So meaning if you don't stimulate the water, as you see in this video, without this falling drop, I mean, then the state of the water is really trivial, really low energy, and it's absolutely trivial. So we can understand what is the effect of the external stimulation, this falling drop, which generates some particular output, those traveling waves. And by establishing this relationship, we can learn a lot about the physics of water. So this is a perfect example where the idea of reverse engineering or reverse modeling, establishing the relationship between inputs and outputs works perfectly, because there is a perfect resting state, so no particular state. Imagine for a moment that instead of that, we have the system water, which is something like this. So this is the resting state of the water. It's more like at the seaside. We have this spontaneously, we have these traveling waves, which are not originated by the external inputs. They are intrinsic to the spontaneous state of water. And of course, then we can still apply this standard philosophy of applying different inputs and observing the outputs. But now it's much more complex, because we need to calculate and to take into account the interference between the underlying spontaneous activity, underlying resting activity, and the activity that we evoke because of our technique of stimulation. And of course, that is a very bad news, because what that means is that we can still apply this philosophy, but we have to correct that, because we have to take into account the underlying intrinsic spatio-temporal structure. But there is also a very good news, which is if it is really that is the case, so I'll give you some evidence that is really that is the case, that we have some very particular spatio-temporal structure under resting state conditions, then perhaps we can learn something about the brain without applying this philosophy. So without explicit doing tasks, cognitive or perceptual tasks. Even more, what we learn is not only general in the sense that we learn something about the large-scale dynamics of the brain, which would be interesting already per se, but I will try to suggest and show you that we also learn something about how the brain processes information, even if we are not processing information explicitly under this condition. And therefore, for that reason, we decided, because it's much more simple, because basically we have to observe just the brain under a spontaneous condition without any particular task, without any particular stimulation, is for starting to construct a mechanistic model at the whole brain level, it's a much more simple situation. And historically was the reason why we started to construct those models based mainly on resting state. So before going to the modeling part, let me try to remember you or to give you some evidences about the fact that the brain is really like the sea. So we have intrinsically this spontaneous type of activity. So there are spatio-temporal structure even in the absence of any task and stimulation. This was one of the classical papers, Peter Fox, the PNAS in 2005, and what you see here is fMRI activity, volt activity, humans for a long time under resting state condition. that was, of course, operationally defined. The human subjects, they are, of course, awake, they are not sleeping, and they are trying to do nothing. Of course, as you know, I mean, this is impossible. So, because when we are in the scanner or someone asks me to do nothing, I mean, I will start to think about kids, my wife, the chocolate cake of my mother, or whatever, but not in a focused way. And that is the importance. And under that condition, what people were expecting is that if I contrast, for example, regions which are really far away from each other, for example, in the anterior or posterior regions, so in this case, the parietal cortex, the region of the parietal cortex or medial prefrontal cortex, what we would expect is that under this condition, they don't need to communicate because there is nothing particular to do. So most of the time, they should be absolutely uncorrelated. So of course, there is activity because we are alive, and there is some spontaneous neuronal activity, but there shouldn't be explicit correlation. And what you see in the same colors, yellow, red, yellow for the PCC and red for the MPF, and even without any mathematics, you see here just by eye, that they go hand by hand. So there is a very strong correlation. So when people observe that, and what they have done is, okay, I take one voxel as a seed and see with which voxels I have the same effect. So how is the correlation between these voxels and all the other voxels in the brain? And what you see is that many voxels, okay, the yellow reddish regions, which are strongly correlated with the PCC. And this is defined what we call nowadays a resting state network. In fact, I mean, this is a very well-known resting state network. It's called the default mode network, involving these two anterior and posterior. Of course, this is not involving the whole brain. If we concentrate on another voxel, which is not belonging to this resting state network, but would belong to another resting state network, for example, the lateral parietal sulcus, all these bluish regions are correlated between each other, but they are not correlated with the first network. In fact, you also see here by eye that the blue is not correlated with the yellow. So this is a very, very, very simple and direct evidence that there are structure under resting state conditions. Of course, I mean, as you can imagine, there were tons of different improved methodologies developed in order to characterize this spatial-temporal structure. Well, at the moment, it's just spatial correlations with better technologies, ICA, etc. And in fact, what people found in the humans is that there are many different, depending on the technology, there are a relatively low number of resistant networks, between 7 and 15, and the most astonishing feature of those resistant networks is that, with the exception of the one that we have seen before, this default mode network, which seems per se not directly related with any kind of task, all the other networks, they have a name. What that means is they have a name because people have seen those networks before. They have seen those networks before during the execution of very particular tasks. So there is an attentional network, a visual network, auditory network, so on. So meaning that under resting state conditions, so without explicitly doing a particular task, we are seeing how the brain is using the regions which are associated with very particular tasks. And that makes the whole business much more interesting, because it means that under those particular situations, we can really even understand how the brain perhaps processes very particular functions. Last piece of evidence before going to the model, and because it's motivating the first features of the model, and that was also a very relevant paper from the group of Markus Reichel and Mauricio Corbetta, published in 2007. That was very relevant because it was the first time that fMRI was used under resting state condition for a non-human primate. This is the macaca mulata monkey. What you see here on the left is a resting state type of activity. Of course, because you cannot convince the monkey to be white inside of the scanner, they anesthetize, light anesthetize the monkey, so that the definition, also the operational definition of the resting state condition is much better. And cannot be confused with any kind of processing of tasks. And what you see is still, in this case, they are showing only one of the resting state networks. You see this strong spatial correlation at the level of the frontal eye field, so frontal regions and parietal regions, which is a kind of visual motor type of resting state network. When the monkey is awake, is in the scanner and is performing a particular visual motor task, what you see is exactly the same. So this is fMRI, bold as before. And astonishing is that what you have seen here, basically at the spontaneous level, is what you see here under the condition where the monkey is really processing a visual motor task. And for me, the most interesting panel is the one on the right, because they are showing here tracing studies. So they're showing the widening, so how the different regions, in particular, they concentrated on those regions, the frontal eye field and the parietal cortex, how they are connected with each other. So it's the anatomy, it's the underlying anatomical structure. And what you see, again, is an astonishing overlap with the functional structure. In fact, what this paper was suggesting is not only that other species has a resting state, also under much more spontaneous and harder conditions, but that the origin of the resting state perhaps is just trivial. So this is the first model without any mathematics, and it's a valid model. The idea is following. I mean, we have activity, and this activity is noisy activity because we are doing nothing at the resting state. But if I pour noise in each neuron, in each voxel, and those boxes, they are connected, those neurons, they are connected through a fiber, then I will induce a correlation between those different source of noises. And therefore, what we are seeing at the functional level, so at the correlation level of activity signals, is just a reflection of the underlying anatomy. So from that point of view, it's fantastic because we understand resting state very easily. It's also disappointing because it's too trivial. And what that means is if we use really resting state at the functional level, we are just seeing the anatomy. That is boring. Okay, I will try to show you that this intuition is partially right, but it's not absolutely correct. And therefore, we have a chance to gain more information when we really observe both. So the first business is really to establish a relationship between static spatial functional correlation, the form of the resting state, and the underlying anatomical skeleton. I always express this relationship. It's a very well-known sentence in philosophy, which actually is from Aristotle originally, but we know that through the translation of Thomas Aquina, and it's quid recipitur ad modus recipientis recipit, which means the container shapes the content. It's trivial, eh? Of course, he didn't say that in relation with the brain, but apply perfectly to this idea of the relation between the structure. Okay, how we do that, or how we start to construct those type of models, which would be able to explain resting state. We depart from the underlying anatomical skeleton. We have different species, very well documented databases. Now, case of the mice, the one of the Allen Institute. In the case of the monkey, there are also different databases expressing the anatomy. In the case of the human, it's not so well documented, funny enough, despite of but we have a non-invasive way of having a good approach of the underlying anatomy, and it's using also MRI, but under the variation of diffusion sensor imaging and doing tractography, so tracking basically the movement of the water molecules inside of the myelinated fibers. We can construct an approximation of the underlying anatomical skeleton. So we can put this in the form of a matrix, so relating the different cortical areas with different cortical areas. We can do this at the voxel level or at the parcellation level and establish this matrix if there is a fiber connection, and even more, we have more information, we can establish the density of fibers. And this is what we call, of course, nowadays the structural anatomical connectome. On the other hand, as we have seen before, coming from the papers Fox and company, we can also express those resting state and those correlations in form of a matrix. This is what we call the functional connectome, and it's the same type of matrix relating the same type of parcellation, cortical areas, but now we are each element is describing the level of correlation between the different pairs of regions. And of course, the goal of the modeling that we need to construct, and we will assume some neurodynamics at the voxel level, which in principle could be just noisy, as was suggested in that paper of Vincent et al. And the key question is, if we have this underlying skeleton and we put our favorite way of introducing noise in a, of course, a biophysical elegant way and so on, but noise at the end of the day, and we put this noise here, what we generate, so the simulated functional connectome, fit the empirical functional connectome. If that happens always and happens with noise, means that that is trivial and it's not so interesting. But what I will show you, that's the very delicate equilibrium, the very balanced working point, dynamical working point, where we obtain really a good fitting between these two lines. Actually, I will show you there are many models. I just selected here one, which is, I think, the last type of model that we were constructing in our lab. All the elements of the model, as I say, was shown in the other picture, is relating the underlying structure with the functions, and the idea is to put your favorite neurodynamical model in each node. In this case, I put a model which is very simple and extremely general. We call this model is a Hoff model. Why? Because the dynamics at each node level is described by a set of equations which is describing a very particular bifurcation, which is called Hoff bifurcation. The equation which describes that is the most simple equation that are able to describe this bifurcation. Therefore, is mathematics is called a normal form of that particular bifurcation. The idea is that there is one parameter, local parameter, that we call A, and if this parameter in fact is negative, what you have is a fixed point, and because we have a noise on top of that, what we have is just noise. So this is the Aristotle hypothesis. So if we are working at that in that region, we will have just pure noise and an elegant. If we are on the positive range of A, what we have is another state, another stationary state, which is from here locally for an isolated node, and it's pure oscillation, like a sinus function. This is called the Kuramoto region. It's pure oscillation for larger A. If we are in between, so near to zero, but this means we are at the edge, at the brink of the bifurcation, we have a mixture between noise and oscillation. So What that means is that with this model, I can describe really very generally the type of neurodynamical activity that I could have at the local level, from no dynamics at all, or very simple dynamics in the sense of just noise, or dynamic that we observe with many different type of techniques, even self-recordings or EEG, MEG, right, which is oscillatory. And we have here the freedom to select with this parameter which kind of dynamic. From that point of view, is of course there is a second parameter, which is the parameter linking the difference connection. As I said before, we have the density of fibers giving us how strengths are the connections between two given regions. But of course, we don't have any information about the underlying effectivity. So biophysically, that means the values of the conductivity. The first approach is, okay, I simplify the system and say all conductivities are equal. Of course, we know that they are not equal. But I assume the same conductivity for all fibers. And what they mean that there is one parameter, which is this global conductivity parameter, or this global coupling parameter, that I have also to tune in order to get the best fitting of the data. That is the business. So now it's very well defined. I have physical and mathematical model with different set of parameters, the local A's and the global coupling, and I need to show that, or I need to discover under which conditions I am able to fit the empirical data at the functional level. We will use, and that is also relatively new and came from a very good paper in 2014, cerebral cortex, from the group of Vince Kalum, where they have shown actually something that is extremely trivial, but like all trivial things are extremely fundamental. I have shown you before with the Fox paper that we have spatial correlation. Those correlations were calculated during the whole session of resting state. So usually are 10 minutes, 20 minutes. So you take the signals during those 20 minutes and you calculate the spatial correlation. This is what we call nowadays, in order to stress the fact that it's just spatial, is the static grand average, because we take the 20 minutes spatial correlation. And of course, we need to fit that. But on top of that, what this picture is showing, and this is real data from the Charité, from Peter Ritter, is if instead of taking 20 minutes window, you take just a very small window, this is just a couple of minutes, 2 minutes, and you calculate the functional connectivity at that window, and then you slide the window, what you see is that this window is changing. In fact, these are the principal components in order to exaggerate this type of changing, this global changing of the windows, and these are just 3 pairs which are randomly picked. So we see explicitly that there is not only spatial correlation, but this spatial correlation is changing in time. So we have spatial temporal structure. And of course, this is more information, and it's more information that we need to fit, and it's good that we need to fit that because that will constrain much more the model. So in order to take into account not only static grand average spatial information as traditional in the field, so practically the whole resting state field was pretty much obsessed with this type of functional connectivity matrix. On top of that, we take this information in form of the idea of Vince Kalum. So we take those windows and we slide those windows, and we construct a super matrix that we call the functional connectivity dynamic matrix. Dynamics because now we moved the window in time, and in each element we put the correlations between the respective windows. So meaning that is the correlation between this connectivity matrix, this local functional connectivity matrix at this position in time and at this position in time. And what you see, this is for a real subject, the result of the modeling that I will discuss later on. What you see is a very nice structure, because when you advance in this direction, symmetric, of course, what you see is that this state, which is originated here, maintain it because it's yellow, but then disappear, then it appear again, then disappear, then appear again. So you have a type of checkerboard. And this type of activity, of course, is describing the dynamics, so the temporal structure underlying state type of activity. In order to compare in the model these two things, I mean, to compare these two matrices is very easy. I mean, you can use, for example, just the correlation of the correlation. Fine. Here you cannot use the correlation of between the two matrices because, of course, there is no reason in the world why we should synchronize it. And therefore, what you do is something more general, also model 10. Then you take all these elements because they are symmetric. You put this in an histogram. You take all these elements, you put this in an histogram, and then you just compare it. And you use it whatever distance you prefer measure for characterizing the difference between two histograms. I use the Kolmogorov-Smirnov distance, meaning that if this Kolmogorov-Smirnov distance is pretty near to zero, we have a very good fitting of the spatiotemporal aspects of the dynamics. Of course, it's not the only measure. Just to give you a flavor of other possible measures, this is what we call metastability. It's a very simple measure. We just take the state of synchronization. This can be measured with mathematically very simply. If you have the phases of each signal in each area, the sum of the exponential of the complex value of those phases, the modulo of that is a number which is between 0 and 1, and has the characteristic that if it is 0, means that all the phases are absolutely synchronized. If it is 1, they are all in phase. So we have a single number which is expressing the global level of synchronization. This is what we call Kuramoto order parameter. And you can use just the mean value of that for describing the level of synchronization, or the standard deviation or variance of this value across time to describe how stable is that. What we call that metastability. How variable is the dynamics across time. How the different states of synchronizations are changing as a function. And of course, this is another measure, a complementary measure describing spatiotemporal time. So let's concentrate now on this part of the results. What you see here is the fitting of the model, in particular the fitting of these three different types of measurements. So the static functional connectivity, the Kolmogorov-Smirnov distance of the spatiotemporal information, functional connectivity dynamics, or the level of metastability. And you see that in a 2D diagram. The X is this global coupling parameter, which indicates how effective are the files. And on the y-axis, you have this local bifurcation parameter. And in order to simplify, at the beginning, we assume, okay, let's assume that all local areas, they have the same bifurcation parameter, just to have a 2D graph. It's a matter of simplification. The nice thing is that if those guys are all in the negative range, means that we have the noise model. If those guys are in the positive range, this means that we have the stream oscillatory model. If not, it's something in between. And what you see here, just by eye, is that the best fitting, so the maximal correlation between the reality and the simulation of static functional connectivity, here, around 0, somewhere here. The maximal fitting of the spatiotemporal dynamics is also consistent here, and the fitting of the metastability of the data in this case was around 0.16, so it's also. In fact, what you see here are three cuts, one for the noisy regime, one for the oscillatory regime, so negative, positive, and one which is exactly at the edge of the bifurcation. What you see is that the best fitting of all three measures, so maximal here, minimal here, and like the data here, is exactly at that region, so near to the bifurcation. which is very nice because what it means is that the neuronal dynamics, which is maximally consistent with the data, is really a mixture between noise and oscillation. So first take-home message. Second take-home message is if I take only static measures, I can say nothing because whatever model I use, noise, oscillations, or mixture, I have always a good result. So meaning it's not so informative. Of course, I have to have a good result. But and even if I concentrate on this region, all this range of coupling are yielding a good result, meaning that it's not constraining my model enough. It's constraining a little bit because it's telling me you have to use A equals 0, but it's not telling me which is the G. If I start to use spatiotemporal measurements, and that means that those measures are extremely useful for constraining, for discovering the underlying mechanism, then we see that now we can constrain very nicely the particular region where the metastability and the spatiotemporal dynamics in form of the FCD is maximally fit. Second take-home message. There is also a third take-home message that I will not stress too much in order to not distract you too much, and is that the level of metastability, so the level of variability that you have in your system, is maximal. In the reality, it's maximal. This is astonishing. There's no reason in the world why we should have maximal metastability. But here you see, because if you are out of the reality, so for example with another G, you are below the real metastability. It's very interesting. Of course, we can do better, and I will not go into the technical details, but you can use machine learning methodologies in order now to optimize for each local brain region. This is one particular parcellation that we use for those data of Petra Ritter. So you see here the whole brain, all the left hemisphere, all the right hemisphere. And what we plot here are the A's. So now we say, okay, we assume that the A's are different. We want to do a better job. So we want to introduce heterogeneity at the level of the dynamics describing each different node. And what this is showing is that the best that what you can do is this red curve, which means that it is around 0, of course, because if we assume that they are all equal, 0 was doing a good job. But if we are really moving away and introducing this type of heterogeneity, the red curve is doing a much better job. And that means that we have what we call a dynamical core, because this is describing at the generative mechanistic level the dynamical characteristic of each single region by using global measurements, static FC, spatiotemporal FCD, metastability. But by using that, then we infer really the underlying mechanistic model. We claim that that is much more informative than the phenomenology per se. Why? Because the phenomenology per se is functional connectivity, the fluctuation of the functional connectivity, and so on. But this is resuming all this information explicitly in a mechanistic model. So it's giving us a mechanistic explanation of why we have that particular phenomenology. And therefore, we believe that, for example, in clinical translational application, would be much more informative than just looking the functional connectivity or just looking any spatial temporal aspect, giving us a causation, an explanation, causative explanation. Just to give you a flavor of that, I mean, I show an application of Parkinson. We have heard in the other talk a lot about Parkinson. I will concentrate on the use of DBS. Probably you know this type of video. I mean, it's not important what he's saying. He's speaking is, by the way, he was an Oxford professor. He got Parkinson and he was successfully treated with DBS. So deep brain stimulation was implanted in the subthalamic nucleus. As you see, he's behaving normally. And now what he will do is he will disconnect the activity of the DBS. So he will be under untreated situation. And what you see, the consequences are really catastrophic. It has the typical extreme tremor of the part. Not acting, this is true. So you see how successful in this case was the DBS. The general rate of success of DBS in Parkinson is the highest one. Well, in chronic pain and Parkinson, it's around 70–80%. Relatively. Okay, I show you this because what I would like to show you is an example of how we use this model, the Hoff model, and with the information that we gain from that model, the dynamical core, so this generative information about the dynamical working point of each brain region. And we were applying this to data that we got from the UCL. And those data are fantastic because we have resting state, of course, in healthy control. We have resting state in Parkinson, which is interesting per se. But those Parkinson patients, they were all implanted successfully with DBS in the same region, subthalamic nucleus. And the beauty of those data is that we have resting state with the DBS on and with the DBS off. And this is fantastic because we can see now the effect of the DBS, not only at the behavioral level, oh yeah, it's acting on the tremor, but we can see really the global effect of a very punctual, particular, local stimulation at the whole brain level. And the effect is really astonishing. Just concentrate on those pictures. I mean, this is just an application. What we are showing here is for the healthy, for the Parkinson with DBS on, for the Parkinson with DBS off, just the histograms of the bifurcations parameters of each brain region. So the dynamical core. As you see in the healthy, the observation that we have already shown, most of them, they are around 0. Clear. When we're assuming that there is only one, 0 is the best fit. And this is the nice per se. So the system, for some reason, is working around the bifurcation. For a physicist, so near critical. But of course, not all are at the edge of the bifurcation. Some are in the oscillatory region. Many of them are in the noisy region. And that is healthy. If we see the Parkinsonian without treatment, so with the DBS off, it's a disaster. And this is very interesting because that means that, of course, I mean, they have major motor problems, which are extremely disturbing, like tremor or the other extreme, rigidity. But they have much more problems than that, which are probably an epiphenomenon of the Parkinson. Because we know, I mean, Parkinson is very well identified, I mean, as a disease of the substantia nigra, which is also local. But the long effect of that disease is affecting the whole cortex. By the way, this is to the contralateral side, for technical reasons, of the implantation of the DBS, and it's in the cortex, only in the cortex, but involving the whole cortex. You see that the effect of the Parkinson is really affecting the whole cortex, which, of course, behaviorally, we were suspecting that something was wrong in the cortex. As you know, Parkinson, they are having not only motor problems, there are many papers showing that Parkinson has problems, cognitive problems, working memory, decision making, reward processing, etc., etc. Of course, because the whole cortex is disturbed. The nice thing, and this is really causality, but it's a causality that we should understand. People target the subthalamic nucleus because all the experimentation of deep oasis from Oxford that's experimented during many years in monkeys and say, look, subthalamic nucleus, I have really a good suppression of the tremor, so I will install the DBS. But what we see, here we are not caring about the tremor or the rigidity. what we see is that we are restoring the distribution of the heterogeneity in the direction of the healthy behavior. And this is causality. Of course, the implantation in the subthalamic nucleus was not designed for that. Of course, this opened the window to very concrete application, because now with the model offline, I can try all possible locations where I could implant the DBS. And on top of trying to get rid of the tremor, which I know is restricted to the area of the subthalamic nucleus, but I can go now perhaps voxel by voxel and say, I want the situation where I restore at most not only the motor consequences, but the cortical activity. And this is a direction that we are. Okay, I want to give you an overview just of how we can go beyond the pure modeling, just to understand healthy or cases, as you have seen, but to use the model in a non-traditional way. This is what we call a perturbative approach. Perturbative approach is a very typical approach in physics, as many of you know. In neuroscience was proposed and very successfully applied by the group of Milano. It was a genial idea of Marcello Massimini. Here you see the cartoonized version of the idea. I mean, you characterize the global activity of the brain experimentally just with EEG, so in a very cheap and bad way. It's not the best for characterizing the whole brain activity. You stimulate also in a very cheap way with TMS. And the idea is very simple. So I see how the TMS is perturbing the whole brain activity. And the way how I characterize this perturbation is in a very simple way. I try to compress that. So I use what they call the Lempel-Sieve code. This is what you have on your laptop. And if you can compress this a lot, means that this simple is very simple, because you can compress that a lot. If you cannot compress so much, that means that the system is very complex. So indirectly, with this perturbation idea, you can characterize how complex is the underlying dynamics. This is the key idea. And just with this perturbation index, which is the Lempel-Sieve code. So how much I can compress. And here you see that if you do this under resting state conditions or wakefulness, looks very complicated. In fact, the perturbation index is very large. You cannot compress so much. If you do this under sleep condition, looks already graphically much simple. In fact, the perturbation index is much lower. And nice is under REM condition, it looks so complex as in the wake condition. If you compare wake with anesthesia, same effect. Here it's much simple. Or in coma, that looks much simpler in minimal consciousness. So vegetative, this is minimal consciousness, which is much more similar. So as you see, it's a very powerful idea that you can say something about the underlying dynamics with this perturbation. And here there is no model. Of course, now the challenge is can I apply model and gain more information? And the answer is yes. Of course, I mean, now the idea is a little bit different in the sense that Massimini was very much interested in what happens after as a consequence of the perturbation. From a physical point of view, that is not so meaningful in the sense that say, well, what happened? I mean, happens. Go out of the equilibrium. Characterize is out of the equilibrium. In physics, the other way around. Say, I don't care. I go out of the equilibrium, and actually, the best way of characterizing the underlying dynamic is to characterize how I go back to the equilibrium. So I don't care really what happens here. It's just I am doing a disaster because I'm applying a crazy stimulation. But how I recover is bringing information. And this is what we can do with the modeling. So you have now the real data, for example, MRI, image of your favorite type of data in your favorite type of brain state, wake, coma, sleep, whatever. You do your model, and now you can perturb your model a lot of time and exhaustively. This is also good from the ethical point of view, because you cannot get the ethical permission to stimulate a person 1,000 times. You want to have 1,000 times because you care about the statistics. So I want to perturb him 1,000 times. And I want to perturb him not only in one node. I want to perturb in all nodes. I don't get the permission. But in the model, until now, nobody cares. So I can perturb the model in different ways, in crazy ways, in order to make sure that I bring the system out of the equilibrium in all possible nodes and many, many, many times in order to have a good statistic. And what we do is we characterize a topological measure that we call integration. Integration is just we take a snapshot like in the sliding window methodology as before, but it's more extreme because we take only the faces, and that means that we don't need a window, we need just one time point. And this snapshot is the phase log matrix, so the state of synchronization of the whole brain. And I can have practically the snapshot for each time point. And we characterize how much integration is underlying this state of synchronization. And this is what we call integration. And you can characterize that with perturbation, without perturbation. Looks very crazy. Seems that there are not a particular trend, but if you do this for many, many, many trials, do the average, so it's the ERP trick. And for different protocols, you can induce synchronization or you can induce noise. So you see that you perturb the integration in the perturbation case, and then you have this decay time. This decay time, one condition or the other, relaxation to the normal activity, is what brings the information about the underlying. Just to give you very rapid flavor of the type of results that you can get. It's using data from Helmut Lauf, Frankfurt, and Enzo Tagliasucchi, fMRI, and the two situations, awake and sleep, in particular N3, so it's deep sleep. And you see here the latency, so the decay time for awake and for sleep. What you see is that you need much more decay, so the system is much more complex for different type of perturbation. It's a perturbation of many nodes, which are randomly chosen. And in all these different type of perturbation, we have a very significant difference in the latency, so meaning that we can identify different states. Well, you can generalize this, and I will not go into the details. I mean, and instead of doing the perturbation, we can consider some internal signals as a perturbation. And this is what we call intrinsic perturbation or ignition. The idea is very simple. You do exactly the same as before. In fact, we use also the integration and so on. But instead of perturbing the brain, we consider some particular event, which is some high activity in the fMRI, for example. So crossing the threshold. And that was shown that it's relevant by many people, Chialbo, and so on. And then in a window, we see the consequence of that particular event. And then we average across all the events. So meaning that we have an information how a particular region, and we can do this, of course, for all regions, broadcast information across the whole brain. Turn out that this information is also significant. So this is the same data as before, awake and sleep, the level of ignition for each node. And you see that they are really very significantly different. In fact, I mean, there is less ignition, less broadcasting of information in general across the whole brain during deep sleep in comparison with awake. There are many other characteristics that are very interesting to remark, but it's another talk per se. This is also to show that it's not only related with the sleep, and it's a very, very interesting application. These are data from the Imperial College, from Robin Carhart Harris. Robin is experimenting with resting state under normal situation, and then the situation where the participants, which in this case are healthy participants, they are taking drug, in particular psychedelics. Psilocybin is magic mushroom. LSD, you know what. And this is the mean value of the ignition across all the nodes. So this is what we have seen before, the sleep. So awake, sleep, there is a reduction of ignition. In psilocybin, if you take psilocybin, there is an increase. If you take magic mushroom, you go high. Here you see that you really go high from the brain activity, broadcasting point of view. This is placebo versus psilocybin, go high. LSD is even more interesting because you go high only when you have background music. And it's known. This is the reason why they use it. Just normal resting state and normal resting state with background music. So if not, you're not a little bit depressed. Not significant, but it's just to finish, I want to give you two snapshots of the perspective. As I say, without pretending to go into the details, but to say two words about the direction that we are persecuting, at least we are following in our lab. One is to involve not only neuronal activity. So as you see, my whole talk was relating basically these two guys, anatomy and function. Of course, not static. I mean, spatio-temporal point of view. I think the main take with the model. But of course, on top of that, we can introduce the effect of neuromodulators for neurotransmitters. And we have information, for example, coming from PET, that we can use in the same parcellation as we use the DTI or the fMRI, which is giving us the information about the density of receptors for a particular neuromodulator. In this case, we use it, for example, serotonin, 5-HT2A in particular, so very specific serotonin receptors. And we introduce, of course, a neuromodulator dynamical system that entangle with the neuronal system, and we see what happens. And of course, where we tested that is exactly with the data that I was showing you before, LSD, and we are able to show that if we use really the PET information and the right PET information in order to show that it's not causality, we use also PET information, but falsify that because we use we shuffle the PET information, so we cheat the system, and we show that the best fitting functional connectivity dynamics, the best fitting is when we use not only the neuronal system, but when we really entangle the neuronal and the neuromodulator. So that's this direction is extremely promising. In fact, it's still not published. And the last direction that I want to mention is what we call the probability state space. As I suggested, I mean, it's very important, as you can imagine, to use the right measurements for extracting the mechanistic information. So functional connectivity alone, grand average, is not enough. I hope that I managed to convince. So we need the spatio-temporal information. But it's also not the best measure. And we were really spending a lot of time trying to think which is the best way of characterizing spatio-temporally, of course, the activity under different situations, resting state, sleep, drugs, whatever, task, health, disease, and so on. And our proposal is that we can do that by extracting the different states and expressing that in probability states. Here we are showing that, in particular, we extract the state by using these snapshots of the phase log matrix. And if we apply clustering, and in this case, we were applying this to coma, vegetative, minimal consciousness, and healthy, or wake of the cover. The data and really collaboration mainly with a group of Jacob Sitt in Paris, but many other groups. Because we use patients from Liège, from Paris, from New York, and from Toronto. And what we are able to show that also here, here in form of the type of Markovian probability scheme, is that different states are associated with different distribution of probability. In particular, different distribution of transition probability. So that means that that is a very powerful idea, a very, very sensitive characterization of the fMRI activity spatio-temporally, that we can use not only for using this as a biomarker, but for trying, in the style of the Parkinson, for trying to reestablish a situation which is near to a healthy situation, not only in Parkinson, whatever disease you want to treat, by stimulation, so by using the perturbation, but by real stimulation, and then you let the system alone to do its own business. So it's a totally different idea and way of thinking, as people think that the stimulation should be used in clinical applications. I mean, because you want to use a TMS or DBS in order to solve really mechanistically, plastically something very concrete. Yeah, one can do that, but it's too difficult. I have no idea how to do that because it's too complex. But if you are happy just to find a location where you stimulate and you put the brain in a good situation, and then the brain alone will per se reestablish homeostatically, plastically, in a complex way that we don't understand, that will go in the right direction. You are only putting the brain in a good situation. Well, I hope that I managed to give you a very brief, rapid flavor of what we can gain by whole brain modeling, mechanistic explanation of activity and all possible situations, resting, and so on. This is extremely interesting not only for basic neuroscience, but also for application. Of course, big thanks to the people, my collaborators, many of them. I mean, I only enumerated a couple of them, where we are getting the data and extremely interesting ideas, and of course the people in my group. Thank you for your attention. So, back for questions.
So, a question in general about more the technical side of doing dynamic functional connectivity studies. So, what are the general scan acquisition parameters that you recommend in a standard resting state study, or is what I understand is generally you want to do 10, 15 minutes, and something like that. Try to amplify and get as much signal as you can, but when you're doing sliding windows, there's very, very small windows of that. So, how do you get over that trade-off?
Yeah, that's a very good question. I mean, that's the reason why, even if the sliding window methodology works, and we use a 1 minute window, so that means if you have a TR of 2 seconds, you have 30 points. So, and you are calculating correlation with 30 points, which is really at the edge of criminality. But in spite of that works. But because I was not so much convinced of that, I mean, we really switched it totally during the last years to the use of this snapshot of the face lock, because then we don't need a window. We can do that really for each time point. So we have one parameter less to tune, and it's and in fact, we were getting much better results for relatively small resting state situation. You know that at least for us, the tragedy is that when we try to apply this in clinical environments, and in basic environments, the resting state is always 20 minutes, 30 minutes. It's fantastic. In clinical environments, you could be happy if you get 5 minutes. And that is really statistical point of view. So we're showing that we are getting better results. Question there. Yeah. Yes. We are using a lot now imaging, mainly because of we have an excellent temporal resolution that we don't have in fMRI, and we have all the spectral, consequently all the spectral information. You use the model exactly in the same way. One have to the way of analyzing is more oriented to the way of analyzing imaging. Until now, you know that the analysis of imaging was extremely biased. Interesting from an epistemological point of view. Was extremely biased by fMRI analysis. So people in imaging were happy if they could reproduce what people found in fMRI, which is extremely stupid because they have a much more powerful technique. And that was very much also influenced with a very beautiful paper I like a lot from the group of Andreas Engel, he et al. In Nature Neuroscience a couple of years ago, where they were showing that you can do exactly the same and recover what you get in fMRI if you concentrate on the slow part of the signal. So you are killing again your nice, beautiful spatial temporal resolution. And that works. So, and in fact, all the papers that were generated in other groups and in my groups for modeling were applying this technique, which I think is stupid, but we were applying this because this is what people in MIT apply. We are now extending that, and because we are deeply collaborating with groups, and we are trying to convince them that say, okay, forget that. Go really, we use now really the nice temporal resolution. And a key question there is to try to answer what is the right time resolution. People believe that still is 0.1 hertz, at least for resting. But now I can check directly. Yeah, if I use a static spatial information, 0.1 hertz. That was the paper. But I know that the cheapest, worst measure that I can use. The question is, can I use another measure? For example, probability state space, where I maximize the entropy of the probability state space. So, beautiful way, the richness of the dynamical repertoire. In mathematical terms, the entropy of the probability state. For which time window, for which time scale, I can reach the maximum of time. And that would be, for me, the determining time scale. We have done that, of course. Published, not even written. Turn out that the optimal time scale in resting state conditions is 200. So much, much lower than what people believe. Absolutely. And also there are many people going in that direction, like the lab of the thinking, I mean, trying to study this, not at the time scale level, but at the frequency, spectral. Different spectral visions imply different. And we have a version of the Hopf model which involves all the different narrow bands with different.
Two questions. The first one is to present for me. You are going to repeat the experiment of the drugs. You need some participants. Maybe it's a general question. It was also surprising for me that we are trying to analyze very complex processes in the brain, activity, dynamical activity, but we are using, let's say, a support linear correlation. I don't know when we can consider that we have a correlation 0.5, 0.6. Um, you comment also the size of the window because the results are quite dependent. So how can we extract the optimum size of the window, the optimum, and if you try some other metrics instead of correlation or
Oh yeah, I hope that that was one of the main take-home message. I mean that I think what's good that people historically started with linear correlation of the static functional because it's the first business that you have to solve. Yeah. And at the beginning we were happy with 0.4, which is not fantastic. Nowadays, I mean, you've seen in the Hof model, we get over 0.8. But in spite of that, we are absolutely convinced, and I try to convince you that this is a very bad measure because it's not so informative. I mean, that you have to fit that, I fully agree, but it's not enough. And therefore, we were looking really for other measurements complementing this type of measurement. The FCD, so the functional connectivity dynamics, is one. Metastability, other one. The probability state space, other one, which are non-linear, are non-correlation. In fact, the probability state space is the most detailed type of information that you can have because you are directly working at the probability. There is no, I cannot imagine more detail. And it turned out that even others, the metastability, you have seen some of the slides, they are absolutely fundamental in order to have to constrain the information. Not a speculation. It is demonstrated. There's still many papers, as you know, in the literature that were claiming that after the first wave of modeling, say, oh, people are applying very sophisticated modeling, spiking, integrate and fire, Wilson Cowan, and all fancy non-linear complex model. And there was a paper from the showing, well, look, I mean, I put noise on the structure and I get the functional information. Only the static. If you want to get more, noise and also absolutely explicit in the Hof model. If you use in the noise regime, yeah, you can explain. Not astonishing because it's too easy, and because it's really too much related with the anatomy. But the challenge is to stress more. That
before you were comparing for TBS, healthy subjects, you had also patients with DBS installed being off and being on. I was wondering if there was any measurement of people who had installed DBS before being actually performed underlying surgery has taken place. Because I mean, DBS, like installation as far as I know in your canal, you can actually damage some fibers while installing it, and I was wondering if there was any measurement of if there was an impact on connectivity or anything.
not in that case because they were not scanned before, or at least we didn't receive the scanning information. But we have done, actually, it was a single case. Was a patient of type assist. Type assist was the one that promoted. And for that single patient, we got, I have to say, only DTI. DTI before surgery, after surgery, and 6 months after that. And what you see is that there was not major change between before and after surgery, which does not mean too much because you know DTI is but at least at that level, DTI was not changed. But the nice feature is that 6 months after DBS implantation, there were changes in the DTI across also the whole. So meaning that because they were reestablishing, this is because the reason why I believe that we don't need to really to fight against reestablishing plasticity in an explicit way. I mean, if you manage to put the brain in a good situation, so those guys, even these 6 months, they have a relatively normal life. And the brain has done the job to establish many of the connections. Of course, I mean, at the end, we published this, I think, in plus one. Because I think the result is as such. Yeah. If the, sorry, again, if the DBS. Or the DBS, I have no idea. I really don't know. We have to ask one of those. If I put the speculate, I think not. Make your strategy. And I don't see that it's deteriorating at all. Why didn't I say? Good. Nice. Thank you so much. Thank you. Pues esto ha sido toda la sala. Hemos tenido una entrevista. Espero que os haya gustado. Más dudas. Entonces, ahora tenemos un coffee break, ¿vale? Y ya tenemos disponible toda la zona de trabajo para coffee break y después de ello ya a las 5 voy. Sí, pues queda media horita más. Sí, voy a sí, claro.